now that we have this notion of double integrals and what they mean, we need an effective way of computing them. We need an effective way to evaluate our double integrals. And so the tool that we're going to use, let me get this set up here, is what we call Fubini's theorem. And note that I've labeled this as Fubini 1. There's going to be, in our next section, there's going to be a Fubini 2. That's a stronger version of this, but we'll start off with Fubini 1. So what this says here, if f of xy is continuous throughout a rectangular region, x is between some constant a and some constant b, y is between some constant c and some constant d. What Fubini's theorem tells us is that we can evaluate the double integral over R as what we call here an iterated integral. So first you integrate, like the inner integration is x runs from a to b dx. So I just cover this up. This is going to be our inner integration. And then once we perform that integration, then we integrate with respect to y. And not only that, but this says that we can do those two integrations. In this case of integrating over a rectangular region, we can do these two integrations in either order. So down here, we first integrate with respect to y. Y runs from some constant c to some constant d. Then we take the resulting answer and integrate that with respect to x. And so these are called iterated integrals. Let me write that here. And the idea is that we always integrate, do the inside integral first, and then we evaluate the outside integral. When we evaluate the inside integral, we're going to be integrating, in this case, a function of xy with respect to x. And so this is going to feel just like the case of partial derivatives that we did back in chapter 14, where if you want to take the partial derivative of a function with respect to x, you treat all the other variables like y as constants and take the derivative. Here, if we're integrating with respect to x, we'll be treating y as a constant. Let's go ahead and do an example of this. So let's evaluate the integral over where r is x runs from 0 to 1, y runs negative 1 to 1 of 2 plus x squared times y. Now, we have two different ways to do this depending on which order we do our iterated integral. There's not a good or a bad choice in this particular case, so let's just go ahead and do one after the other. So for the first one, let's do a dy dx integral. So that means that our inside integration is going to be integrating with respect to y. So y is going to run from negative 1 to 1. X is going to run from 0 to 1 of 2 plus x squared y. Note that you don't have to put, let me just point out here a little bit of notation here. I'm putting an x is equal to 0 to 1, y is equal to negative 1 to 1 to remind myself, which bounds here 0, 1 correspond to x, and which bounds negative 1 to 1 correspond to y. You don't have to do it because the dy and the dx, these over here tell you that the inside integral these are y bounds. This tells you the outside integral is with respect to x. But I find it to be helpful, especially in future sections, to keep track of what's going on. Okay, so how do we go ahead and do this? Okay, so first we integrate this with respect to y. So antiderivative with respect to y is going to be 2 becomes 2y. x squared, we treat that as a constant here. So x squared times the antiderivative of y will be y squared over 2. And then we plug in y runs from -1 to 1 dx. Okay, so what happens now? We plug in 1 and -1. Plugging in 1 gives us 2 times, and this is plugging in y is equal to 1, not x equal to 1. That's a common mistake. 2 times 1 plus x squared times 1 squared over 2. So that's x squared over 2. Minus, now we plug in -1, 2 times -1. And we plug in -1 in there. So -1 squared becomes +1. So we again have an x squared over 2. And the thing inside here, this all simplifies down. Those terms cancel. We have 2 minus -2 is 4. Okay, and so what is our final answer here? Integrate 4 from 0 to 1. We just get 4. Okay, so that's our first example of iterated integrals with Fubini. But Fubini promises us that we can do this in either order. We did the second one down here. Now let's do one where we integrate with respect to x first. So same problem. Just integrate with respect to x first. So the y bounds will be from -1 to 1. The x bounds will be from 0 to 1. 2 plus x squared times y dx dy. Okay, so now we do this first. And what do we end up with? Integrating this with respect to x. 2 becomes 2x. X squared goes to x cubed over 3. Y is a constant. So x squared y becomes x cubed y over 3 when we integrate with respect to x. Plug in x is 0 to 1 dy. And what do we end up with here? Plugging in x is 0 and x is 1, we get 2 times 1 is 2, plus 1 cubed y over 3, plus y over 3. And then when we plug in x is equal to 0, we get zeros. So these terms go away, and now we need to integrate 2 plus y over 3 with respect to y. So 2 becomes 2y. Y over 3 becomes y squared over 6. So when we plug in y is equal to -1 to 1, we get 2 times 1 is 2, plus 1 squared over 6, minus plug in -1, 2 times -1, plus -1 squared over 6. And when you crunch this out, you again get the 4, which is the same thing as before. So Fubini's theorem promises us that the double integral over this region can be evaluated using either of these iterated integrals, and we see in this case that we get the same answer. Okay, so that is our first use of Fubini's theorem, and I think it's good here is 15.1 pre-class problem number 1. So evaluate the integral, the double integral over r of x plus y squared dA, where r is x runs from 0 to 2, y runs from -1 to 1.